Hello and welcome back. This is our very first video about acids and bases. And this video is going to go over basic definitions. First, we're going to list some strong acids and bases. So let's split this up. We'll have acids here, bases there. I believe we should have 7 acids and 8 bases that you need to know. So if you'd like to pause and see how many you remember, now would be the time. But we need to have HI, HBr, HClO4, HClO3, of course, HCl, H2SO4, and HNO3. Our bases will have NaOH, KOH. We're basically going to have all of the alkali metals paired with the hydroxide. Rubidium hydroxide, cesium. And then we'll also take some of the alkaline earth metals from calcium down. So calcium hydroxide, barium hydroxide, and I always run out of space for this one, strontium hydroxide. Alright, so there are your strong acids and bases. You will want to be able to recognize those. So let's go over some basic properties. Acids tend to taste sour. I would not recommend that you actually taste acids unless it's a food. So like vinegar has acetic acid. Fruits have citric acid, and lemons, that makes them taste sour. Bases, however, will taste bitter. If your parents ever made you put soap in your mouth for saying bad words, then you would know this taste. Poisonous plants tend to taste bitter. Broccoli, bitter. Baking soda, whose formula people need to remember, so let's write that down. NaHCO3, sodium bicarbonate. And soap, again, bases feel slippery, so soap feels slippery. If you spilled some sodium hydroxide on a bench and then you got some on your hands on accident, your hands would feel slippery and you'd want to immediately wash them. Bases tend to react with oils in your skin to form soap. If you have seen Fight Club, you might be thinking of a particular scene that involves soap. Blood is basic and it is buffered. We will be going over buffers at some point here. And here's a specific example. Drain cleaner can contain potassium hydroxide. And we don't put acids down the drain because acids react with metals. And so if we were to put those down the drain, they would eventually eat away at our drains, which is not good. Not good at all. You could test to determine if something is an acid or a base. So in order to test if something's an acid, you could use litmus paper. It would turn red. They taste sour. You could add a base to see if it neutralizes it, and use the litmus paper to see if it worked. You could use a flame test. We know that acids react with metals, and we'll see if hydrogen gas is produced. Oh, my base one isn't showing up. That's weird. So you could test if it's a base by using, so let's put that on here, base. You could use a litmus paper, and it would turn blue. You could remember blue for base, red for pain, although bases could cause pain, so maybe that doesn't work. They taste bitter. Again, I do not recommend that you taste these chemicals if you don't know what they are, but technically you could taste it, and then again you could add an acid. Whoops. Acid. Okay, well, I'm giving up there. Let's try that again. Acid to neutralize it. Okay, so that's how you could determine if something is an acid or a base. There are 3 types of acids and bases. These, for those of you in my class, are going to go on your definition page in your acid-base notebook. So make sure that you have this information written somewhere. So we'll start with Lewis acids and bases. Yes, this is the same person who is named for, or this is the same person that Lewis structures are named after. So according to Lewis definitions, acids are electron pair acceptors, whereas bases are electron pair donors. So here we have boron trifluoride and ammonia reacting to form this really complex compound. We'll go over naming for that later. So boron trifluoride is a Lewis acid, whereas ammonia is a Lewis base. And if we draw the Lewis structures, we would see that. So let's try drawing them. We have boron, fluorine, fluorine, fluorine. You need to count up the valence electrons for each of them. Boron has, I don't have my periodic table. Let's see here, 3 valence electrons, whereas each fluorine has, let's see here, 2, 4, 6, 7. These are valence, but then there are 3 of them, so I multiplied that times 3. So this molecule will have 21 plus 3, 24 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And ooh, boron has this empty space here. Interesting. So now I'm going to draw ammonia, where nitrogen has 1, 2, 3, 4, 5 valence electrons, whereas hydrogen, we know each one has 1, and there are 3 of them, valence electrons. So if I add that up, that's 5 plus 3 is 8. So nitrogen, hydrogen, 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 2, 4, 6, 8. So now you might see that this nitrogen has this lone pair here, and boron has this empty space here, and so our Lewis base is going to donate electrons, and our Lewis acid is going to accept electrons. So this is our acid. Well, this is our base. So if you ever want to check if something is a Lewis acid or a Lewis base, you could just draw Lewis structures. Arrhenius is our next person of interest. He defined acids and bases slightly differently. An Arrhenius acid is a substance that, when dissolved in water, so aqueous, increases the concentration of hydrogen ions. So here we have a generic acid, HA, and it is aqueous, and it splits up into hydrogen and A. And this right here showing up tells us that the concentration of hydrogen ions has increased because we have more of them in our products. An Arrhenius base is a substance that, when dissolved in water, increases the concentration of hydroxide ions. So here is a generic base, BOH, and we end up with more hydroxides, again this is aqueous, in our product. So it has increased the concentration of hydroxide ions. So here are some real examples. We have hydrochloric acid and sodium hydroxide. Hydrochloric acid will completely dissociate in water. It's a strong acid, and the hydrogens will be released, increasing the concentration of hydrogen ions. Sodium hydroxide will release all of its hydroxides and increase the concentration of hydroxides. There are, however, some problems with the Arrhenius definition. For instance, it is only true for bases that contain hydroxide ions, and there are some bases that don't even have hydroxide ions but still make solutions basic, like ammonia. This does not have hydroxide. And baking soda, do you remember what baking soda is? It is NaHCO3. Again, no hydroxides. There is another problem with Arrhenius acids and bases, which again isn't showing up on my slide. That's really strange. And it's only true for reactions that take place in an aqueous solution. Oops, let me see, aqueous solution. So the solution must be aqueous. Those are our problems. All right, almost done. Now we're going to go over Bronsted-Lowry. This one is used most of the time. This is the big one. The Bronsted-Lowry model states that an acid is a hydrogen ion donor, whereas a base is a hydrogen ion acceptor. When a Bronsted-Lowry acid donates a hydrogen ion, a conjugate base is formed, and when a Bronsted-Lowry base accepts a hydrogen ion, a conjugate acid is formed. So every base has a conjugate acid, every acid has a conjugate base. And these two substances are related to each other by the donating and accepting of a single hydrogen ion, and we'll call those conjugate acid-base pairs. I'll give you a visual example so it's a little less confusing. But first, let's just note that the hydrogen ion and the hydronium ion are used interchangeably. In other words, they mean the same thing. Hydrogen, hydronium, same thing. So here is a little bit less of a confusing example. So here we have an acid, HA, and HA is going to donate a proton. So now it's missing that hydrogen. It's not there anymore. It has donated it. We know we can think of hydrogens as protons. In case you forgot, let's write that up here. Hydrogen is basically a proton. So this acid is going to become this conjugate base. And the reason why it's labeled as a conjugate base is because in this reversible reaction, if I was to go in the other direction, look at this A negative. It would be able to accept a hydrogen if you went in the other direction. So something that accepts a hydrogen or accepts a proton is called a base. So that's why an acid, when it reacts, creates a conjugate base, whereas a base will accept a proton and become a conjugate acid. Now this guy has a hydrogen that if you went in the other direction, it could donate that hydrogen. So it is now a conjugate acid. So here we have a conjugate acid-base pair, conjugate acid-base pair. And up here, again, we have another conjugate acid-base pair. You'll want to be able to identify these. So let's practice. This is asking us to identify the conjugate acid-base pairs in the reaction. So let's see, we have HClO2 plus water reacts to form H3O and ClO2. So here, this guy is our acid. It has a hydrogen, and the reason I know it's an acid is because when you look over on the other side of the reaction, that hydrogen is no longer attached. It has donated a hydrogen, donated a proton. So now it no longer has that proton, donated a proton. So this is our acid, whereas this is our conjugate base, because now it could accept a hydrogen if it goes in the other direction. And then here our water is acting as our base. Weird. And if you look, oh, look at that. It accepted a hydrogen. So this is our conjugate acid now. That's a little hard to read, but all of these words beneath this example are saying what I just said. So now this is your chance to practice, so I would highly suggest that you pause right now and try it on your own. So go ahead, pause. Okay, I hope you paused. If you didn't, shame on you, pause. Otherwise, welcome back. So let's label our pairs. Here I have HCl. We know that's an acid. So let's find the chloride ion. here. This is a acid conjugate base pair, so I'll label it acid conjugate base. And water, here let's use green, green is nice. Water looks like it accepted a proton, so that means it must be a base, and this would be a conjugate acid. All right, let's do this again. Hydrochloric acid, definitely an acid, so it is linked with the chloride ion. That's a conjugate base, whereas this is an acid. Ammonia, we know, is a weak base, and ammonium, oh, looks like it accepted a proton. So that definitely confirms that ammonia is our base, and this is our conjugate acid. All right, last one. Water and ammonia. Well, let's start with ammonia. We know that ammonia is going to get linked with ammonium. And it looks like in the process it accepted a proton, so that means that this is our base and this is our conjugate acid. Well, that means that water must in this case be acting as an acid. That's a little weird because wasn't it just a base in one of the previous slides? But that's true, water can act as either an acid or a base. So let's do this. And started off with 2 hydrogens, ended with only 1. That means it donated a hydrogen, making this our acid and this, our conjugate base. So this is all about donating and accepting protons, also known as hydrogen ions. And that's the end of our first video. Thanks for listening.